The Compton effect. Based on the photoelectric effect, scientists started to ask questions, and you may have the same questions as to where is the energy coming from? So you're shining light on a metal in the photoelectric effect, and these electrons all of a sudden have kinetic energy. And if these electrons have kinetic energy, they have velocity, they have mass, and therefore they have momentum. Well, in our first unit, we talked about momentum, and the major concept there was the conservation of momentum. So in other words, if these electrons now have energy, they have mass and velocity, therefore they have momentum, then there must have been momentum before. And in other words, in the photoelectric effect, that light hitting the metal surface, that must have had momentum. So a scientist named Arthur Haley started asking these questions. Does light have momentum? And he was doing this experiment. Let's go down here. He had a piece of graphite. That's not graphite. A piece of graphite, and he was shooting X-rays at it. X-rays that had a certain wavelength. And he noticed that after hitting the graphite, the X-rays would be scattered at different angles, and they would have a longer wavelength. So here they would have a longer wavelength, and if they have a longer wavelength, it's a form of electromagnetic radiation, EMR, then they must have had, if this increases, then this must decrease, correct? So they must have had a lower frequency, and if they have a lower frequency based on this formula, they have less energy. And if they have less energy because of the conservation of energy, that energy must have gone somewhere. And where did it go? Well, Mr. Compton detected electrons being ejected from the graphite. And these electrons had kinetic energy. They had velocity, and they had mass, and therefore they had momentum. So because of the conservation of momentum, Compton theorized that this right here must have had some momentum. And how did he articulate what that momentum was? P equals h over lambda. So this is a new formula for us. This is the momentum of a photon, or the momentum of electromagnetic radiation. The momentum of something that doesn't have mass, which is a very foreign concept to us. But Haley came up with this idea that light has momentum, which really makes sense. We've already proven that light has energy. It only stands to reason that it also has momentum. So we now have a new formula, P momentum equals h over lambda. That's the formula for electromagnetic radiation, or something that doesn't have mass, and then here's the formula for something that does have mass for momentum. Okay, and you can go over his the details of experiments. Here's his formula right here. Here's the explanation. Page 2 goes through the explanation, talks about the conservation of energy, the photon theory of light, the conservation of momentum. And so here's what happened. You've got an incident X-ray, hits the graphite, bounces off at a different angle, has a longer wavelength, therefore less frequency, therefore less energy. Where did that energy go? It went to giving this ejected electron some energy. Okay, and here's our new formula. P equals h over lambda, Planck's constant over the wavelength. That is for the momentum of an X-ray, or some EMR, some form of EMR. And then he did all these calculations. He came up with this new formula, and it worked out. It says in your notes, it worked out really well. It said it was almost spooky how well this formula worked out. And this is a formula on your formula sheet. It's probably the most bizarre formula. It says delta lambda, which means the change in wavelength, equals h over mc times 1 minus the cosine of theta. So that is the 1 minus the cosine of theta is very simply the angle right here with which the X-ray comes out of the graphite. What's unusual in this formula is the h over mc. They're all constants, h Planck's constant. The m is the mass of an electron, and c, we all know, is the speed of light. Mass of an electron, this is the speed of light, which is very unusual, isn't it? It's very unusual because we know that nothing that has mass can move at the speed of light. We believe that. And therefore, it's very unusual to be multiplying the mass of something with mass, two s's, times the speed of light. But again, this concept, the Compton effect, it kind of really reinforced the wave-particle duality of light. And Compton is one of those theories that prescribes to the particle theory of light, as is the photoelectric effect, and then we have all the wave properties of light. And so the wave-particle duality of light is our present belief or a present description of how EMR works. And here's our your classic Compton question. It's a great question because it goes right back to the first unit. It's really the only reason for having momentum in the Physics 30 curriculum could be right here, because this is a conservation of momentum question. Make sure you leave a lot of space on your page because it's a very long example. We'll go through it nice and slowly, but it's a great review of the conservation of two-dimensional collisions and the conservation of momentum. So we have an X-ray light source that has the wavelength of that. Its graphite scatters at an angle of 15 degrees from the original pass. Have determined the wavelength of the scattered X-ray and then determine the velocity of the ejected electron. So once again, we have a X-ray. There's the incoming X-ray. When it comes out the other side, it has a longer wavelength and it's scattered at an angle of 15 degrees. 15 degrees. And then out comes an electron, right? Electron comes out. Doesn't say anything about the angle with which it's ejected, but we can calculate that using the conservation of momentum. So the conservation of momentum says the momentum over here before equals the momentum after. And as you can see, before, we're just talking about the momentum of the photon, and afterwards, we're talking about the momentum of the photon and the electron, the combined momentum of those. So it's a very simple two-dimensional collision. And let's start off by calculating the initial momentum. So step one is the momentum before. Momentum before. And before, we're just talking about the momentum of the incoming photon. That will simply be P equals h over lambda divided by and that gives us 5.18 times 10 to the negative 22 kilograms times meters per second, which again, it should make you feel very uncomfortable because now you're using mass in something that doesn't have mass. So that's the only way we can express it right now. So that photon has this momentum, kilograms meters per second, and that's the momentum before. Now we need to calculate the momentum afterwards. And the momentum afterwards, what does it tell us? It doesn't tell us the wavelength of the scattered ray. So it doesn't tell us what that wavelength is. So we can't go to this formula right away. We need to find out what that final wavelength is. And that's where we're going to have to use, in step two, we're going to have to figure out the wavelength of the scattered ray. Using Compton's formula. Okay, and everything's a constant there. The only thing we need is the angle, but let's just plug the numbers in anyway. And remember, we're talking about the mass of the electron. Speed of light. And if we plug all that into our calculator, we end up getting 8.266 times 10 to the negative 14 meters. And remember, that is delta. That is delta lambda. That is the change in wavelength. But we don't want the change in wavelength. We want the final. We want the scattered ray. We want the wavelength of the scattered ray. So we always know that the change in anything equals the final minus the initial. And we're trying to find the final. So it will be simply be the change in the wavelength plus the initial wavelength. The initial wavelength is 1.28 times 10 to the negative 12, and that gives us a final, the wavelength of the scattered ray is 1.36 times 10 to the negative 12 meters. And from that, so now we have the wavelength of the scattered ray. From that, we can calculate the momentum of the scattered ray. The momentum of the scattered ray is going to be this, divided by the wavelength, 10 to the negative 12, and that gives us a momentum of 4.87 times 10 to the negative 22 kilograms meters per second. So let's just take a minute and see what we've calculated. We've calculated the momentum of the scattered ray. We calculated the momentum of the initial ray. Right. And because this is a two-dimensional collision, we then have to take that one, the second one that we calculated, and we have to separate it into components. So 15 degrees gets scattered at a 15-degree angle, and this is its momentum. And we need an X and a Y component. I mean, just like all the two-dimensional collisions that you did in the first unit. And I'm just going to skip steps here, and you use sine and cosine just the way you always have. And I'm going to tell you that the X components of this is going to be 4.7 times 10 to the negative 22. And the Y components of this is going to be 1.26 times 10 to the negative 22. So that's the X component and the Y component of the scattered ray. And now we can go and calculate the, I don't know, step one, step 3 here. Let's go with step 3. We can calculate the X and the Y components of the electron. All right, let's just go back to our initial diagram so we can see. So there we go. We've calculated the initial momentum. We now have the X and the Y components of this. And now we can calculate the X and the Y components of the electron based on the conservation of momentum. We know that this was all horizontal. The initial momentum was all horizontal. And if the scattered ray had now has a horizontal momentum of 4.7, if initially it had a momentum of 5.18 times 10 to the negative 22, now has a horizontal momentum of 4.7 times 10 to the negative 22, then the X component of the electron must be what's remaining. So again, the initial momentum of the X-ray was all horizontal, and it was 5.18 times 10 to the negative 22. The final momentum of the X-ray is 4.7 times 10 to the negative 22. Therefore, the X component of the electron must be oops. Sorry, I know I have a habit of mixing things. So, and if you subtract those, you get 4.8 times 10 to the negative 23. That's the X component of the electron. The Y component of the electron is actually very easy because we know that the scattered ray had no Y component. Sorry, the initial ray had no Y components. The scattered ray has a Y component of this number here. Therefore, the Y component of the electron must be that same number, but in the opposite direction. I just put a negative for now, which just means it's going, according to our diagram, it's going down, which makes sense. Now, what I find really interesting is how much down is it going? You'd think, oh, this is just a little X-ray hitting a graphite and it bounces off 15 degrees. The electron has mass. It probably bounces off at a very shallow angle. Well, no, in fact, it bounces off at a huge angle, because if you look at the difference between these numbers, this is times 10 to the negative 23. This is times 10 to the negative 22. So this number here, the 1.626 times 10 to the negative 2, is much, much bigger than this number right here. So now we're going to do a triangle, right angle triangle for the electron. We're going to solve that triangle. The resultant vector will give us the resultant momentum of the electron and the angle. And I'm just going to, video is getting really long, so we want to R equals R. Turns out to be 1.35 times 10 to the 22. But that's a momentum, and we want the velocity, so then we have to go to our there's your momentum. Your mass is the mass of an electron, 9.11 times 10 to the negative 31. And you end up getting a velocity of 1.48 times 10 to the 8 meters per second, which is insanely fast. Once again, it's actually half the speed of light, because light is 3 times 10 to the 8th. So it's really fast, and then you will solve for the angle. Just go over here. The angle turns out to be 69 degrees. So your answer is 1.48 times 10 to the meters per second, 69 degrees below the horizontal. Okay, hope we didn't go through that too fast, but you can watch the video again and review your two-dimensional momentum questions, and that is the Compton effect.